streaming/recording as well, so we get that going. All right, can you all see my other screen, the quiz 3 is what we're looking at? Okay, so I had a look at these this morning. You guys universally nailed question number 1, so kudos to that. Everybody's got type 1 and type 2 errors down. Type 1 error, you think you found something, but you didn't. You reject the null hypothesis incorrectly. Type 2 error, you thought you didn't find something, but you should have. So a miss instead of a false positive. So we've got those. Next question was related to power. So 1 minus type 2 error is your rate of power. So given an effect size to be found, such as a correlation of 0.3 was what we used in the example, power is the probability that you will find it in a given sample. So there was some confusion on this answer for number 2 about the things that go into power. The 3 things that can increase your power, so increase the probability that you will detect an effect of a given size being significantly different than 0, is sample size. That's the big one. Mo people, mo power. How many people do you need for your study? More. Always more. Some of you work with large-scale data sets. You might actually have too much power, meaning that everything is significant and you have to choose some other way of deciding what to talk about. But most of us, that's not the case. So more people, more power. What else goes into power? Looking for 2 more things. Eagerly watching the chat window, or you can talk, your choice. What else goes into power besides sample size? Yep, we got the answers right here. So alpha. So if you want to increase your power, do you make your alpha go up or down? This is a gesture one we can all participate with. So does alpha go up for more power or does alpha go down? Yeah, up, up. So increasing your willingness to make a type 1 error decreases your chances of making a type 2 error. So increasing your willingness to make a type 1 error translates into more power, because what you're doing is making it easier to find something. You're relaxing the standards for what you would consider unexpected, or the threshold for declaring significance. But practically, you cannot move alpha up and be taken seriously. That is true. But in thinking about whether to set, say, a 0.05 versus a 0.01 versus a 0.001, those choices have implications for power. So there is some upper bound. I've probably never seen an alpha level of more than 0.1. I'd say that 10% alpha is probably the upper bound before someone starts to yell at you. Incidentally, one-tailed test is another way that people can increase their power, because what you're doing if you select a one-tailed test, let's say that you say you want a 0.05 and you want a one-tailed test, that's the same as a two-tailed test with an alpha of 0.1. So it's kind of like cheating, because you're loading up one side of the distribution with the 5%. It's actually 10% if you were to take into account the other side. So we got sample size, alpha, and then the other one is effect size. Thank you, Diana. So effect size, the strength of the association. So you can think of this as how large the correlation is. In a chi-square, it's hard to think about that be the size of an odds ratio, perhaps, or the size of a risk ratio. In the context of testing a sample mean against a population mean, it would be the difference between the two. There was some confusion with respect to variability. So the variability of your variables doesn't directly influence your power, because effect sizes are standardized. So a correlation, for instance, is a measure of association that's already been corrected for differences between the means of the two variables that you're correlating and their variances. So an effect size is in a unit that already takes into account how much variability there is. So variability per se doesn't affect power. Okay, so questions on that or comments? A few of you noted that you were not sure about your answers, and I had to laugh because I have a memory of this topic back when I was an undergraduate and the first time that I was exposed to this. In psychology, I was lucky enough to have three different research methods and statistics classes available at the University of Nebraska, all taught by a wonderful bear of a teacher, Cal Garvin. He's like this big human teddy bear. And he's the one that I stole my line, "How we doing?" with the hands like this, like that's him. I'm channeling him. But he was my stats teacher. And I remember taking a test in one of those classes where we had to talk about type 2 error and power and type 1 error. And I was just sitting there staring at this and I could picture the overlapping circles in my head and I couldn't come up with it. I knew they were related, but I know they weren't like the opposite of each other. And so I just wrote down, sorry, Cal, I don't have this yet. That was my answer for how to define type 2 error. And he gave me 1 point out of 4 for honesty. That was my score. So, yes, Madeline, do you know Cal?
Yeah, peripherally, my friends who took classes with him loved him. He's like, people love him, so.
Yes, Cal Garvin. He is the originator of the homework system, by the way. He was the one who gave me the idea, and his graduate student who programmed it, David DeWester, gave me the starter code. And so I took it and ran with it inside SAS. In case any of you are curious, I use SAS to do all of the data simulation, coding of answers, and it actually writes the web pages that run everything as well. So SAS is amazing. So shout out to my history and my colleagues. All right. So I didn't get it at first. If you don't have it yet, that's okay. Caitlin, glad I picked SAS. Well, someone else will tell you that you should have picked R. So I'm still R will forever be on my to-do list of like things I need to learn. I just haven't like bit the bullet to do it yet, but it's on there. So, and I'm sure Stata could do something like this too, but I came to Stata much later in life. So, try to teach me R. It's fun. Okay, so R is fun. You heard it here first. It's R has a steeper learning curve than the other packages. That's why, even though it's free and that's why people love it, I've chosen not to use it because there's a lot more um, things that you have to sort of already know for the commands to make sense. But anyway, I'm off on a tangent. So are we good with power? Okay. Last question then. Definitions. So I promised you that you didn't have to memorize any formulas this semester, right? Right? Yes. I'm not expecting that. And you don't have to do proofs or derivations or anything that's super math heavy. Rarely do you have to do a hand calculation. There's one or two, but the emphasis isn't on that. Instead, I want you to memorize definitions because the faster these things come into your brain when you hear the word slope, right? If it's automatic what that means, you'll be able to follow whatever I'm saying about the slope much more readily. If the idea of, say, what a slope is a little bit shaky, then in trying to remember what a slope is or what it does, then you're not as able to attach other pieces of information to it. So as quickly as you can, please commit those three definitions to memory that I'm asking about in question 3. So an intercept. Always, always, always. The expected value of the outcome when the model predictors are 0. That is what it is always going to mean, not only in this class, but in every other stats class. It never changes. So what happens if you don't have any predictors? Right? There's a special type of model that we talked about last week where you don't have any predictors. Do you remember what it's called? Mean is related, but what's the model called if you don't have predictors? Empty. Yes, empty model. And that is a term that is used in other classes as well, in particular, what's known as multi-level models, where you're trying to analyze variability across different dimensions of sampling simultaneously. But the empty model has no predictors. So if your model has no predictors, if it's empty, your intercept is then just the grand mean of the outcome. Think of it this way, if you don't know anything else about a person, your best guess as to what their outcome value is going to be is just the mean, because that's the most likely. So the process of building models then is to try and make your best guess for each person more specific, more informed by the predictors that we're going to add to the model. So intercept expected outcome when your predictors are 0 specifically. That's why it's going to be important to make sure that 0 is a meaningful value in the scaling of your predictors. We'll talk about that in just a second. Okay, with me so far? That's another cow, by the way. How we doing? And with me so far? Always with a hand gesture. This. This is my however finger. This is my although finger. This is how we doing. It's like my own version of sign language. But all right, slope then. Slope from algebra, rise over run. Change in y per unit change in x. The reason, as I said on the video that I recorded, change in y versus difference in y. I like the term the difference in y for a 1 unit difference in x if you're talking about cross-sectional data. So if you have a person who has an x value of 1 and you're trying to talk about a different person with an x value of 2, those people differ from each other in their x. They don't change into each other. So a change in x is sort of weird if you think about it as a cross-section of different individuals. In longitudinal data, so if people are measured repeatedly, for instance, you're studying grade schoolers and you measure them once every grade, then you can talk about as a change from second grade to third grade because the people actually are changing. So that's a nuance of language that not many people would be picky about, but I'm one of them. So you can say the change in y for a unit change in x, or you can say the difference in y for a 1 unit difference in x. Either of those is correct enough for present purposes. So unit difference in x. That means that we have to think about what a unit is. And the word unit is a generic term that should always be replaced with something that conveys what x represents. So dollars, years, counts, like whatever a unit is a better way of interpreting a given slope. So change in y for a 1 unit change in x, that's a slope. Okay, residual. Now this is one that you may not have seen in algebra class. I don't remember talking about residuals in algebra. Do you? Anybody? No, because we were just making lines and functions, right? We didn't really care. But the idea of a residual is an acknowledgement that whatever prediction you're going to make from your model for a given individual, it's not going to be perfectly right. It's always going to be off. So if I have an empty model, then the residual is how far off each person is from the sample mean as the best guess. Once I put a predictor in, it's how far off each person is from the regression line drawn by the predictor. So the definition of a residual is always the same idea. It is the difference between what the model says y should be and what the data says y should be. It's how far off. So you can think of this, if residual isn't an intuitive enough word, you can think of it as a discrepancy. A misfit is, that one makes me squishy for reasons that I don't want to get into because that refers to a whole different set of classwork. But misfit is sufficient, I think, if you think about just missing, like someone's not going to be exactly on the regression line. E for error. So you will see that used a lot. It's the error of the model, but it doesn't necessarily mean you've done something wrong. Like the term error implies that you're at fault. Like you should have gotten this correct. Like, no, people are different, right? Even people with the same level of education or the same gender identity or the same whatever, they're going to differ from each other in other ways. And so it's just a discrepancy across individuals relative to what has been predicted. That's residual. And we don't really care what E sub I is for each person. We care what the variability in the E's is. And our objective is to take the total amount of variability in an outcome, so that's what's given by the empty model, and make it smaller by putting in predictors. So the discrepancy between what the model says and what the data say should decrease as you add predictors to the model. Makes the model better. Okay, questions or comments on any of that? Yes, Deborah, go for it.
Can you just tell us one more time what you said we have to remember? The definition. So I was jotting. I was trying to write it down.
Okay. Definition of a residual is how far off the real outcome is from the one that's predicted.
Okay.
Y
What
sub
about,
I minus Y hat.
and the intercept? What was that one?
Expected outcome when the predictors are 0. And slope is 1 unit as change in Y for 1 unit change in X. Those are the 3 things that if you commit them to memory, it will make your life easier. Okay. Other questions or things you want to hear again? All right. So did you guys watch the video I made last week? You can nod even if you didn't. I have no way of knowing if you did or not. I can see the number of views on YouTube, but it could very well be other random people from around the world. My channel has about 300 subscribers. So, free content, right? But on there, I left you with a riddle. So I'm switching now to lecture 3 here. This is slide 14. So let me put this up here. Do you know where this map is from? Here, let me make it bigger so you can see that.
Airport.
This is an airport, but which one? This is Terminal B of a very busy airport.
I'm guessing Chicago.
Nope. Good guess, though.
Atlanta.
Atlanta, yes, that is
Atlanta,
correct.
yeah.
Yes. So once upon a time, my husband and I were in long distance relationships when he worked at the University of Georgia and I worked at the University of Nebraska. So I got to know the Atlanta airport quite well. And the first thing that I would do when I got off the elevator in search of whatever version of Chinese food they had at the Atlanta airport. That's my go-to for airport food generally is Chinese. You got to know where you are before you can know how to get to the Chinese food, right? The "you are here" star is the most important part of the map. It's your way of locating where you need to go relative to where you are. So I'm using that as an analogy to think about what the intercept is going to mean in our models and why it's important that the predictors that we have in our models have a meaningful 0 value. So here's an example from the data that we're going to be playing with where the outcome variable, as I said, is income or money, annual income for an individual, and the predictor variable that we're playing with is years of education. So as you might expect, there is a positive association between one's education level and one's income level. More education leads to more money. The regression solution. So that phrase regression solution refers to what the estimates are for the betas. These betas are known collectively as fixed effects. The word fixed means everybody gets the same. They are constants. Beta 0 is the fixed intercept, and beta 1 is a fixed slope. Starting next week, or the week after, I think we're going to have more than one slope in the model at the time. And after churning through the data, the best estimate of what each of these fixed effects is worked out to be minus 7.89 for the intercept and 1.82 for the slope. So let's think about this in terms of the units of measure here. X is in years. So a unit of X is an additional year of education. Y is in thousands of dollars. So a unit of Y corresponds to $1,000. So this model is telling me that somebody is predicted to make negative $7,000 according to the model. How can that be? A grad student. Ding. Yes, these are supposedly working adults, but yes. We're not talking net income, right? We're talking gross here. But how can that be? How can you make negative $7,000? Yeah, well, who is the intercept referring to? Like, where is the star in the airport map of these data? Yeah, no years of education. So that's what I've tried to draw here. I actually had to extend the regression line that SAS made me to get all the way down to 0. So arguably, a reference point of nobody who exists in your sample is not that useful. So we're going to fix it. We're going to fix it with a linear transformation. And this particular kind of linear transformation is known more generally as centering. In general, centering is either adding or subtracting a constant from everybody's score to change what 0 means. The most common centering that you will come across is what's known as mean centering, where you insert the sample mean and you deviate scores relative to that. So you're making a new column in the data set. Rather than picking the mean, I personally prefer to pick values that have some sort of ready interpretation so that I can think about the reference person for my regression line. And so I picked 12 years of education. In this current US sample, that corresponds to a high school degree. So if I change where 0 is, then I am moving my intercept all the way up the regression line now to where 0 is. So note the change in the scaling of the x-axis. So the variable that goes into the model is education minus 12 as a new predictor, a new column that I've created. So now the intercept is 14. A high school educated person is predicted to make $14,000 a year. For every additional year of education, you are predicted to make another $1,800, 1.8 as the slope, per year of education. That's what the model is telling me. So note that the slope is exactly the same between these models. Homework question. Because centering does not change the slope. When you only have a linear slope of a predictor, it changes the intercept. And you can choose any place along this x-axis that you want your 0 to be. There are no wrong choices, but there are weird ones. In more advanced models, you can make a choice that results in the model not converging, like it couldn't find the answers, but not in these models. So picking something that is within the scale of the x-axis as the definition of your 0 is helpful in creating an intercept that actually means something. If you have an x variable, a predictor, that already has 0 as a meaningful point, then you can leave it alone, such as number of times something has happened to you, right? There may be people in your sample that something has never happened to. That 0 is a legit 0, and you can think about them as your reference person, and then what happens to them for every additional time that something happens. So are we good with this so far? So we're in every model that you're going to see with me, not only in this class, but in every class I teach. The predictors are going to be adjusted as needed so that 0 means something, so that the "you are here" sign for the intercept is within the scale of the data. So then let me get to this slide. This is slide 17. I want to do this one for you just to review what E means then. So I'm going to show you how to fit these models and get all of these numbers from SAS and Stata later today. So that's where these came from. It's not like I'm omniscient and I just made these up, right? These came from a real data set. So if I have, starting with an empty model for income, money, as my outcome variable. Empty model has no predictors. So it only has a fixed intercept and a residual. So the things that I want to know, the parameters that I'm trying to estimate, the values to be found as part of this process. One of them is going to be the value of the fixed intercept, and the other is going to be the variance across people in the E's. So that's what we pay attention to. Is there a way to minimize the top toolbar? You would think. Hide floating meeting controls. Yay! Thank you. I didn't know I could do that. The newest update of Zoom has all kinds of fun things. I also discovered in my conference, mind you, that I went to of quantitative psychologists, that you can also do things like this. There are filters. Yeah, so it's under filters. Now everybody's going to want to go play this, but yeah, I can be cool while I teach my class. I can be ironic. So yeah, video filters and things. I don't think I could handle this. So we're going to go back to none for now. But yeah, that's the other thing I learned in my conference last week is that you can do video filters on Zoom. So important stuff. But anyway, so the two things we want to know out of the empty model, what is the fixed intercept and what is the variance across people in the E's? Now, the reason that we want to know these things, the fixed intercept is our jumping off point. If we don't know anything else about a person, that's our best guess as to what everyone's outcome is going to be. So in this picture, that is given by the horizontal, purple line. That's my prediction for everybody. So this slide is focusing on demonstrating what's going to happen for this predicted person out here who has a score of 8 on education. So note the scaling here. A score of 8 corresponds to education of 20 years because I've centered education at 12. And they have an income, a reported income of about $60,000 here. So we're focusing on this person. So an empty model gives the same predicted outcome value given by the fixed intercept, which is just the sample mean for everybody. So that works out to be 17.3. Well, this individual is way above average. Why are they above average? No idea. We don't know anything about them yet. But if we take the E for each person, so each of these dots, and deviate it from this line, some of the dots are going to be below the line and have negative E's. Some of the dots are above the line and have positive E's. So that's why we have to square the term for variance so that the positives and negatives don't cancel each other out. And this, if you figure it out what it is for each person, so take the deviations, square them, sum them up over the sample size, and divide by n minus 1. So this n minus 1, by the way, is called denominator degrees of freedom. It's the number of things we had to calculate in order to figure out where we are. Right now, we only had to know the sample mean, so that's why it's minus 1. The total variability across people in these E's is 190. So that number is all of the reasons why people have different income levels. That's all the variance that we have to explain. Our job is to make that 190 go down so that we understand why it is that some people make more money. So why is it that some people might make more money? Because of education. So the best fitting regression line through education looks like this. So note the way that I'm expressing my model. My x variable has an I subscript because education varies across individuals. And I have the minus 12 here so that the reader who's looking at this equation knows what 0 means. So this is conveying my centering. It's telling the reader that the reference person for what this beta 0 fixed intercept now means is someone with 12 years of education. So that reference person has a predicted income of 14. That's the middle here. And then for every additional year of education, their predicted income goes up by 1.8. So I'm cutting down the precision here to keep the numbers easier to work with. Well, this person out here has a value of 8 for their predictor. So that works together to give them a predicted income level of 28.4. So this little TP thing over the Y hat, that's a term that means what the model says your outcome variable should be, the predicted Y. So anybody in this model who has the same level of education has the same predicted outcome. So rather than just guessing the mean for each person, we're guessing what's known as a conditional mean. It's a mean factoring in where you are on this x-axis. But it's not going to be perfect. So there's a big spread, for instance, among the people who all have 8 years of education, just like there's a big spread amongst the people who have 6 years and so forth. Well, this particular individual is still off by 30. So we've made it go down. Their prediction is off less. Their residual, their discrepancy between the data and the model is smaller. And collectively, it's smaller for the whole sample to the extent that this line is not flat. If the line were flat, if there were no relationship between these variables, if there was a Pearson correlation of 0 between these variables, then you would expect the variability from the empty model to be the same as the variability after I put in this useless predictor, to the extent that the line is not flat, either positive or negative, right? This is negative for you guys? Okay, I'm trying to get my arm motions because it's backwards for me. To the extent that the line is not flat, then the total variance of the e's should be less after you put in the predictor. And so we can carve up the discrepancy between this one person and the mean into pieces now. So the distance between the sample mean and the regression line, that discrepancy has been explained by the model. So this person is supposed to be up here because of their education level. So part of the reason why they make more money than other people is because they're more educated than other people. That's part of it. But that's not all of it, because they still make way more money than they're predicted to for people with the same level of education. So the unexplained part then is what's left. And so as you add predictors, the part that is unexplained should shrink and shrink and shrink. And we're going to be able to characterize this as a proportion of variability in the coming weeks. We want to know how much of the variability has been explained relative to all the variability that we started with from the empty model. Okay, how are we doing? Okay, then, all right. So what we're going to be looking for then to characterize our slopes. Slopes are unstandardized measures of relationship. This slope in particular is a linear slope, but we'll get to nonlinear ones later. Here's the stuff that we're going to look for on the output. An estimate. That is the value that characterizes the slope itself. So the 1.82, for instance, the change in y for a 1-unit change in x, that's the estimate. We are going to get directly as part of this process a standard error. So standard error conveys the expected inconsistency across samples for the slope in the same way that it conveyed the expected inconsistency across samples for the mean. It's the exact same concept. The estimate divided by the standard error is going to give us a test statistic. So from now on, you're not going to hear me say t-test statistic anymore. There's a shortcut for that. It's t-value. It's easier to say and it's easier to write. So t-test statistic has become t-value. The formula for it is exactly the same as what it was when we were testing a sample mean against a population mean. It's what you got, so your sample estimate, minus what the null hypothesis said it should be, and in this case we're testing against a null of 0, divided by the standard error. So t then gives you a standardized version of how far off your sample slope is relative to a null hypothesis slope. And the null hypothesis slope most often is 0. Doesn't have to be, but it most often is. Because we're using t, we need to have denominator degrees of freedom to go with it. So t, remember, is flatter when you have fewer people. So we got to know how many people, that's n, and we got to know how many terms we had to calculate in order to do this test. So k is a new letter we're introducing that's going to keep track of the number of fixed effects. So in this context, we have a fixed intercept and a fixed slope. So it would be n minus 2. Can you guess what would happen if we had a fixed intercept and 2 slopes? Then it would be n minus 3. And if we had 3 slopes and an intercept, n minus 4. Yeah. So it's kind of like, how many points did we have to spend to get to this model? That's what our t-value is going to be referring against. P-value Same as before. That's the probability of getting a result as extreme as we got if the null hypothesis is true. And so you will get an exact p-value that corresponds to the location of your slope relative to the null hypothesis of 0. And you can also get a confidence interval where the software does the work of figuring out what the t-critical value needs to be, and it also does all these computations for you. And because slopes are unbounded, we don't have to do any of the R to Z transformation stuff that we had to do to get confidence intervals for a correlation. It just works out with the unbounded metric just fine. All right, so here's some math. I'd like to show you where this stuff came from. So hang on one second. There we go. Do you want to see how to make SAS and Stata do this stuff for you? Why not, right? Let me put it this way. Would you rather get your calculator out or see how to make SAS and Stata do this for you? Yeah, see, when you put it that way, right, it's all about SAS. So in all seriousness, it's always better to let the software do it for you because it's going to carry more digits of precision. It's going to not screw it up. Even as careful as you could ever be, you're probably going to screw it up. And if you have more than like 5 people doing things by hand, it becomes impossible. And after you leave this class, see, I'm already assuming that you're going to come back, right? Like if you come back and hang out with me next spring, the models that I'm talking about for longitudinal data next spring, you literally can't do hand calculations. The estimates are found through iterative search algorithms that do not necessarily have what's known as a closed form. Like there's not a formula that you can use and an answer pops out. So very quickly in statistics, you leave the world where hand calculations are even a thing. A phrase, by the way, I'm happy to report I have taught my 5-year-old. He says that all the time now, and he uses it accurately. Mommy, is that even a thing? So I am killing parenting. All right, but here's my thing. Example 3. So do you all have this? This is a separate handout. It's a PDF. Like example 2, there is a zip folder that goes with it that has the original data, the full syntax, and the full output in both programs. So when you go to do homework 3, you can open up those example files and you don't have to type all this stuff. You can copy it over and start it as a template. So the same process that we've been using, I'm using here to import the data. So I'm defining, this is SAS code starting with here. I'm defining a file save. This is what it looks like if you're using someplace that is not the H drive inside the virtual desktop. So I'm defining where my data set is. I am then referring to it down here. The data set is called GSS example. When it comes out, it's going to be called example 3. I am adding formats. So one of the variables that we're going to be working with is binary, version of marital status. I'm adding labels. So there's going to be 3 variables in total for this example: the binary marital status, years of education, which we've just been talking about, and income, since we've just been talking about. I'm then applying the variable value labels for the binary categorical variable. And then one more thing here that you haven't seen yet, I don't think. This is new. So this is not something you need to worry about for homework, but it is something that you need to worry about in life. Okay, everyone's paying attention. Yes, in life. This shit is serious now. In life. So here's what happens in life. Not everybody answers every question that you ask of them, right? For whatever reason, you have missing data. The bad news is that any case that doesn't have all of the variables in your model is not going to get used in these analyses. It's what's known as list-wise deletion. So in this case, if I'm going to have a model that has education as a predictor and income as an outcome, then they need to have those 2 variables to be included. The second part of this is going to have marital status as a predictor instead. So what I am doing here is asking it to go through those 3 columns of my data and check whether or not the people have a value for each of the three variables. I'm doing this as a function. So nmiss is a built-in function that counts the number of missing values across the columns that you put in the parenthesis. So what I'm saying here is a conditional statement. If the number missing for these variables is greater than 0, meaning if they're missing a value of any of those three columns, then delete. Can you guess what happens? Yeah, they're gone. Yeah. Now they're not like gone forever. Remember, we're working in a temporary directory. The original file is safe and sound someplace else. So the reason that I'm doing this is that I want to keep my sample size the same across all of the different models, regardless of which variables I'm using. Otherwise, people are going to drop in and out. And if there's enough missing data, then that can cause inconsistencies as to what type of results you're finding. So this is a strategy that's designed to simplify the confusion that missing data can cause. Is this the best strategy? No. But the ones that are more complicated are going to be a few classes away. But to keep the sample constant across all of the models I'm going to show you, I am selecting it for the variables that I'm eventually going to need. That way everybody is going to stay in or out, and they don't drop in or drop out depending on what the model is. Okay, so questions on that idea? Okay, Stata folks, same process for you. File save. I was running this version of Stata on my desktop, so it doesn't have the client slash thing on the top of it. The import command to import the Excel sheet. We're defining the value labels for the marital status variable, labeling the variables, and then the analog to do the selection of complete cases is a little bit different, but it's very similar. Stata is first going to generate a brand new variable that I've named nmiss. So that's going to be a new column. The analogous function is called rowmiss. It counts the number of missing values across the same row for the columns that are given in parentheses. And so it's going to store this as a new variable. And then I say if the number missing is greater than 0, drop, which is the analog to delete. So it takes 2 lines of code instead of 1, but it accomplishes the same goal. So just to reiterate, you don't need to worry about this on your homework. Your homework has complete data because your homework features fake people, and fake people are very compliant. They answered all the questions. But for life, I wanted to give you this as a way of making sure your sample stays constant. All right, so even though you already know how to do this, I am re-demonstrating. Is that a word? Re-demonstrate? I think it is. How to get descriptive information for your variables. So in your homeworks, I may ask you to do this even though you've already done it, because I want to make sure that you maintain the ability to do this. So for descriptive statistics for quantitative variables such as income and education that we're currently playing with, proc means, or in Stata, the analogous command is summarize. So this gives us the descriptive info for the variable that is to be our outcome. So here's the variance of 190 and the mean of 17.3. You're going to see those numbers come back in the empty model in just a second. And education has a mean of 13.8. So if I were going to center education, and I wanted to use the sample mean, I could do that. I could take a new column and have it be education minus 13.8. There's nothing wrong with that. However, to me that's weird, because do you think that any of the people in this general social survey wrote down that they had completed 13.8 years of education? No, unlikely. So I prefer that my model reference for the intercept, the you are here sign, is an actual person that would have given me an actual value. So I'm not going to use 13.8, but I am going to use the rest of the information to figure out what a reasonable guess would be, and I'm going to pick 12. There's no wrong guess. It's within the middle of the data. It corresponds to a ready interpretation. That's why I'm going to pick it. Making some pictures, something else that you may want to do in life, but not necessarily needed for homework, just to show you what these things are looking like. So distribution of income is positively skewed to start with. So I just want to make the point that this is not normal, but that's okay. Likewise, education, also not normal. I don't even know what words I would use to describe that. It has a lot more people on the upper half than on the lower half. Neither of these variables is normal. When we look at them marginally like this, that's okay. The point that we're going to get to with income is that what the model is assuming is that the residuals are normal. We don't know what the residuals are yet because we haven't fit any models yet. So it's okay if the outcome variable doesn't look normal to start with. It's what it looks like at the end that matters. The other variable that we're going to look at is binary marital status, and it looks like this variable is split 55-45 in this case. Correlations between the variables, so measures of bivariate association, also something useful to do when you're beginning your modeling process. So income and education, do a little review here. What's that number right here? Tell me. It's 0.38. This is a correlation matrix given to me by SAS or Stata. First off, what is that number? I'll give you some letters. Is that N, P, T, R, or K? What do you think? Got a couple guesses. We got R versus P. Those are the closest. Yeah, this one is R. P is underneath it. So this 0.38, that is my Pearson correlation coefficient. It is a measure of the linear association between education and income. The fact that it's positive means that as education goes up, income goes up. The value underneath here, a p-value less than 0.0001, means that if the null hypothesis of zero correlation were true, we would see a correlation this extreme or more extreme less than 0.01% of the time. So this correlation is significantly different than zero. We would say the correlation is significantly, because of the p-value, positive because of the direction of the R. So not everyone has finished homework 1 and 2 yet, but trying to review some of those answers as to how you know what is what. By the way, if you have questions on homework, I'm happy to talk to you individually about those. So this is the number that our slope in the model is going to be trying to tell us about. We will see this number come back as what's known as a standardized slope, an effect size within these models. In the second half of this, we will also see whether income is related to marital status. So this one is a little bit tricky because marital status is 2 categories. The way that this is coded, you have to know in order to interpret this correlation. You got to know who's higher. So I'm going to scroll back up to my labeling conventions, and in that variable, 1 is unmarried and 2 is married. So when you think about as X goes up, that means as you're more likely to be married than not married. Coming back down to my correlation then. So people who are married, that's my analog as X goes up in this binary variable, have higher predicted income because this is a positive correlation of 0.22. And we know that this correlation is also significant, unlikely to be found if the null hypothesis of no correlation were true. And then last but not least, education and marital status. How would I describe that number? you've got 4 choices: significantly positive, non-significantly positive, significantly negative, or non-significantly negative. We got to vote for 2. Non-significantly positive, that's also number 2. Non-pos, an abbreviation, very nice. Yes. Non-pos it is. So the non part comes from the p-value. So the p-value needs to be compared to alpha. Alpha, traditionally 0.05. That's what it's going to be on all your homeworks because that's what it is in life most of the time. So the fact that this p-value is greater than 0.05 means we're in non-significant territory, well within expected sampling fluctuation if the null hypothesis were true. So we know the result is non-significant. We know that it's positive because the correlation estimate is positive. Okay, any questions on that review stuff? Okay, here's some confidence intervals for those. Here's what it looks like in Stata. Very, very similar output. And Stata has an extra thing you have to use if you want to do confidence intervals for correlation. Okay. New stuff. One new command for the rest of the semester in each program. That's it. We've got them all. Proc GLM in SAS and regress in Stata. Everything we're going to do is going to fit under one of those. So we're going to fit an empty model. Now, would I do this in life? For these type of models, no. So this is more of a pedagogical step designed to get you used to the idea of thinking about variability and what happens to that variability as you add predictors to the model. So here's my empty model. It has no predictors. It has a fixed intercept as one of the parameters that I care about, and the variability of the e's across people as the other. So first in SAS and then in Stata, proc GLM. You know what GLM stands for? Yeah, it's on the slide. So, oh, and this thing came back again. There we go. General linear models, yes. So the term general, just to review, means that the residuals have a normal distribution as part of the model. Linear means that it's in a form of constant times variable plus constant times variable. And model means that some of the variables are predictors and some of them are outcomes. So GLM, just like in all the other procs in SAS, you need to tell it what data set you're working with. So for instance, if you take this snippet of code to make it work for homework 3, you need to change example 3 to homework 3. This is an option that controls how many characters of names are printed on your output. SAS truncates variable names by default, and so I don't want it to do that, so I'm saying print up to 100 characters. Model. This is where we write out what we want the model to do for us. And the formula looks exactly the same as the code. Okay, I just did some sort of weird formatting that I'm not sure how to do. But model, and then the word income, that refers to what y is, what your outcome variable is. So that's what you would change in homework 3, whatever the outcome variable is. For instance, I'll give you a hint. It's going to be a fit count. You're going to be playing with the same preschool data inspired by my son, who is still a student in Miss Beth's class, and she is a saint. Miss Sanzi, if you're listening, we owe you the world. She is a saint on earth. Miss Molly is too, but I've known Beth much longer. So if you're predicting, say, the number of fits thrown as your outcome, that goes here. So it's what goes in the equation as well. And then after the equal sign is nothing. That's because the empty model has no predictor variables. You get a fixed intercept by default. You don't have to ask for it. After that, the slash is separating off options for what output that you get. And the output that I'm requesting, believe it or not, the answers are not printed by default. You actually have to ask for them. That's what solution means. It means give me what the fixed effects are supposed to be, please. Alpha and CLPARM are asking for confidence limits around each of my fixed effects using 95% confidence or 5% alpha. And then the last thing here, some of the procedures in SAS need both a run and a quit. You would think that's redundant, but it's not somehow. So we do need both of those to shut this thing off and make it go. And this title right here is shutting off this title up here. So you don't have to use titles. They just help label your output so that if you're scrolling through it, you can find things more easily. The title here just shuts off what was the title first. That way it doesn't keep printing over and over and over again. Okay, so questions from SAS people on this little piece of code right here, procglm, our new friend. Okay, Stata people, you're going to love this. Here's yours. That's it. The word regress with 2 S's. What comes first after it is the outcome variable. Because there's no predictors, that's it. And the comma is used to separate out what's in the model from options, and level 95 corresponds to an alpha of 0.05 for the confidence intervals. So that's it. Titles in Stata, you can use the word display to have it print the title to your output, and you don't have to shut it off. It does that automatically. So, all right. Any questions on those 3 words from Stata folks? 3 words. Okay. So the output from each of the programs then is down here. It looks similar in structure, but I want to point out just a few differences of where you're going to find things to be able to do your homework. So we'll start up here with SAS. This table right here, we haven't talked about most of it yet. I am deliberately not talking about it yet until it's relevant. But there is one number in this table that is always going to be relevant starting now. It's this one right here. It's in a column that is called mean square and a row that is called error. Mean square error. I will tell you later what that means in more detail, but for now, I will just tell you that is what your residual variance is. The variability of the E sub I residuals across people, the 190. So in the empty model, the variability across people in the residuals is all of the variability that there is to be had in the variable. So when we ran descriptives on this variable for income, it said the variance of that variable was 190. That's what this is telling me. So this is our naive jumping off point where everybody's best guess is the same value. It's the sample mean. And lo and behold, here is that sample mean down here, the 17.3. That's the mean of income. So you will get this table for your fixed effects, the betas, and SAS labels the fixed intercept as intercept. The first column is the estimate. So that is the value that is the most likely value given your data in your sample. Standard error is the next column. We'll get to where that comes from in just a little bit, but it's the same idea as the standard error of the mean. It would be how far off the intercept would be in any one sample from the population version of the intercept. So the wiggliness across samples, same idea. If you take this estimate, the 17, divide it by the standard error, that gives you the third column, labeled t-value, because SAS didn't want to print t-test statistic any more than I want to say it. F it, it's t-value. And we're going to have F pretty soon too, so F it is actually not a swear word. T squared is F. Stats humor. Ba-doom. So my t-value. So my t-value is 33. That means that my intercept estimate is 33 standard errors away from 0, which corresponds to a p-value of this. Now, do I care about that? The answer is no. What this is telling me is that the mean income from the sample, which is what the fixed intercept represents in this empty model, the mean income for the sample, that mean income is not 0. So these people make some money. That's what I've just learned. So we're not going to pay much attention to the p-values for the fixed intercepts because they're rarely of interest. Here's the confidence limits for that estimate of the intercept. And this out here, by the way, beta 0, that's not SAS. That's what my other students have called Proc Lisa. That's me being nice and trying to label these things for you. So if you're looking for the interpretation column on the output, that ain't there. That's why I have a job. Because it's not there. Okay, so SAS folks, are we good so far? So the numbers you need to find are in bold. That one, that is residual variance. This one, that's your fixed intercept. The estimate for it. I will also ask for standard error, most likely, as well as T and P. Stata folks, your set of tables is very similar, except that your mean square error is labeled residual. Same idea, same number though. And your fixed intercept is labeled underscore CONS for constant. So it uses the linear algebra language of the constant and the slope, even though the slope is also a constant, which is why I don't like that language. But Stata calls the intercept the constant. And it will always be last in your list of fixed effects. Rather than estimate for the first column in SAS, Stata calls it a coefficient. Standard error is the next column, just like in SAS. T is the third column, so it's the coefficient divided by the standard error. And then the p-value, it only prints to 3 decimal places, and here's the confidence interval. So very similar looking output across programs. The rest of the table we will get to when we have more than one predictor, when it becomes relevant. We're not there yet. Okay. All right, how are we doing? Okay, so I will show you what it looks like when you forget to center your predictors. So this is some homework troubleshooting for you. In homework 3 and beyond, we're going to be fitting models. The first question that I'm going to ask you for any model that I ask you to fit is, what is the residual variance? If you get the residual variance wrong, you do not have the right combination of variables in the model. You've got the wrong columns in there. If you get the residual variance correct, then you've got the right variables. But you may not have the right centering. So this is demonstrating what happens when you put in a predictor that is not yet centered. So original education, in which 0 means 0 years of education. So in SAS, education goes after the equal sign on the model statement, before the slash that separates the options. In Stata, it gets listed second. So Stata folks, order matters. The first column listed is the outcome variable of the model, and the next variables listed are the predictors. You wouldn't know that unless you read the documentation, because there's nothing that tells you that, but you just have to know. The first one is the outcome, the second one and follows are the predictors. So when I put in education, my residual variance goes from 190 to 162. So there's less variability that's unexplained than before. That's good. But I get this weird intercept of negative 7.8. So if this happens to you in your homework, if you have the right residual variance, but you have the wrong intercept, odds are good you don't have the right predictor centering, because the intercept depends on centering. So in this case, the intercept is the expected money for someone who's never been to school, way outside the data. So here's the code that I used to make this picture. Not something I expect you to do in your work, but I wanted to provide it so that you can see how to make pictures. So let's fix it. So the new equation then refers explicitly to the predictor in its centered form. So that means we got to make a new column. So step 1 is to make a new column in which education is centered at 12. In your homework, I will give you the constant that I want you to center with. In life, you would pick this after looking at the descriptives for the data and generally picking something that is within the span of the observed variables for your predictor, observed values, I should say. So in SAS, all data transformations have to happen inside a data step. So this is opening up the data set in the work library called example 3 and saving it as itself. I am then asking it to make a new column. And the way that this code works, the same is true, by the way, for Stata. Hang on. Too many pictures. We'll get there in just a second. New variable equals old variable. So my convention in making new variables that have centered versions of them is that I always make the centering constant part of the name. I stick it on the end, that way I know which one it is. So educ12 is my version of education centered at 12. And so education was the original column's name. By subtracting 12, I'm making a new column, and then I'm giving it a label. And so then inside my model goes education 12 as the new predictor. So now 0 refers to somebody with 12 years of education as the model reference point for the intercept. And since we don't have time to go over all of the output, let me just look at the Stata Code. Stata folks, here's the analog for you. To make a new variable, you need the command gen for generate. But it's new variable equals old variable. There's no semicolon, but otherwise it's the same. And then I put the new centered version of the predictor in as the second column on the regress line. So income is the outcome to be predicted. Education 12 is the name of the predictor. All right. Questions on any of that, since we're just about out of time? Okay, so then what we're going to look at next time are the results of the model, not just what the fixed intercept and slope end up being, but how we can ask the program to give us predicted outcomes for any kind of person. So that's what these extra lines are doing, is asking Stata to do other math for us. That way we could generate pictures that show our results of our analyses, not just parameter estimates. All right. Any questions before we adjourn? No, you all look so sad. Have you lost your will to live? Have we hit that point a little bit? Yep. And now you understand why this is not a 3-hour class. Because I lose my will to live during a 3-hour class. I can't imagine. Yep. So this is why, because we're all done right now. I can see it on your faces. So come back Thursday after a few nights sleep and we'll play again. How's that? Okay, take it easy, guys. I'll see you Thursday, office hours later if anybody wants me.